Hello, if you're watching this video, this is my first boiler exams video I've ever created, so thank you for joining me. Today we'll begin with the first question of spring 2024 for MA166 or Calculus 2. So what is this question? Find the slope of the tangent line to the curve r equals 2 cosine 2 theta at the point 1 comma pi over 6. So let's begin. I'll start by writing the formulas in the corner, or actually the equation. So our function here is r of theta is equal to 2 cosine 2 theta. Sorry, I need to put something under that. 2 cosine, wow, my writing really sucks. Hang on, 2 cosine 2 theta. You know what, I'll leave it at that, and sure. So 2 cosine 2 theta, and the point that we're looking at, I'll call it P, is equal to 1 comma pi over 6. So when they ask for the slope of the tangent line, I'll be very clear. Slope is not equal to dr d theta. What dr d theta is asking for is how quickly is my function leaving or approaching the origin. So in this case, if I have a function like this, I draw it like that. If the function continues on, it's leaving the origin. It's not like approaching it. And you can clearly see that from the function. That's what dr d theta is looking for. Rather, dy dx is what we're looking for. The actual slope of the tangent line, rise over run. So, how do we get from r to dy dx? Well, let's look at our trig triangle here, our polar triangle. We have our triangle here, our hypotenuse is r, and this means that this would be r sine theta, r cosine theta, which conveniently is also this point over here and represents both the x and y coordinates. So x equals r cosine theta, y equals r sine theta. And so we have an r here and we have an r here. We're looking for how to equate these two. So we can essentially call these both the same r. This means that we have to isolate the r in both these equations. So this becomes x cosine theta equals r, y cosine theta equals r. So that means that x, if you sub everything back in, this would be x equals 2 cosine 2 theta, cosine theta. I multiplied the cosine theta out from the left side into the right side. Y equals 2 cosine 2 theta, sine theta. Those are our two equations now. So now all you got to do is you have to find their rate of change, respectively, with respect to d theta. So that would be dy, d theta first. We'll start with that since it's y over x. Would be product rule. It would be negative 4 sine 2 theta, sine theta, plus 2 cosine 2 theta, cosine theta. We do dx here. Dx, d theta, is equal to negative 4 sine 2 theta, cosine theta, minus 2 cosine 2 theta, sine theta. Now we evaluate at these points, or at the point 1 comma pi over 6. However, we notice that our function is not even dependent on r, so we don't even need to worry about the 1. All I have to care about is the pi over 6. So if we plug this into, okay, well, raised for function is not working on me right now. Y prime of pi over 6, we get negative 4. This is sine of pi over 3. That would be root 3 over 2. Sine of pi over 6, 1/2, plus 2 cosine of pi over 3, that's 1/2, times cosine of pi over 6, that'd be root 3 over 2. So we just said negative 2 times root 3 over 4. Cancel this out. 1, 2. This becomes negative root 3 over 2. We can do the same thing for x, x prime of theta. We plug in pi over 6 for this. And this, okay, get out of here, SolidWorks. Hang on. This becomes negative 4. Sine of pi over 3 would be 1/2. Cosine of pi over 6 is root 3 over 2. Yes. Yeah. Okay. Well, actually, no. Sine of pi over 3 is actually root 3 over 2. That's my mistake. I don't know why I said that. So then this would be minus 2 times cosine of pi over 3. That's 1/2 times sine of pi over 6. That's another 1/2. You get the gist. We'll just combine everything. 4 times 3 over 4. Cancel this out. That becomes 1 minus 2 over 4. So this is essentially negative 3 plus 1/2, which is negative 7/2. Back to our formula for before, we said that the slope of the tangent line is dy over dx, but we can also rewrite that to literally be rise over run. So dy d theta over dx d theta. And I mean, if you think about it, you can pretty much take that from the definition of a derivative, which is the delta f over delta x, essentially. Same thing here. So we have negative root 3 over 2 over 7/2, which becomes root 3 over 7. So the slope of the tangent line at that point is root 3 over 7. Okay, welcome back to question 2 of MA 166, spring of 2024 final exam. We're going to be looking at question 2 today. Choose the picture which best represents the curve defined by the following equation in polar coordinates. R equals 3 cosine of 4 theta between 0 and pi for theta. So I'm going to quickly write everything out on this whiteboard. So we have R equals 3 cosine of 4 theta. And that is between 0 is less than, theta is less than or equal to pi. Okay, so I want to quickly review polar coordinates. So polar coordinates are defined by 2 components, okay? For everything, for each point, it would be your radius and then the theta value from the origin, okay? So knowing that, let's start solving this problem. Now, you may be deterred by the fact that you have to draw this out, but I want to remind you that the best way to do this is just to keep plugging in various numbers. So I'm going to draw out my polar coordinate system here, and we're pretty much just going to go in intervals of pi over 8, and so we should get a good result. So let's start. We'll start with theta is equal to 0. When theta is equal to 0, we get r equals 3 cosine of 0, and that equals 3. So when theta equals 0, cosine the function equals 3. So our first point would be out here. Now before I continue on, I want you to notice there are no negative signs in the function. So we can pretty much intuit that if your angle is moving upwards like this, your function is probably also moving upwards like this. Okay, so let's just keep that in mind as we continue. So our next angle is theta equals pi over 8. That results in 3 cosine of pi over 2, and that's equal to 0. So our next point would be at the origin. So I'm just going to quickly draw this out. It would look something like this. Okay? Now we have theta equals 2 pi over 8. We got 3 cosine of pi, actually. 3 cosine of pi is equal to negative 3. Now, I want to remind you, we are plotting along theta equals pi over 4 as our theta value, but because it's negative, we're actually going backwards. So for this third point, it would be towards out here. So now our function would look something like this. Okay, theta equals 3 pi over 8. So I'll just keep doing that until we have a good idea of what this function may look like. So our next one was 3 pi over 2. Cosine of 3 pi over 2 equals 0. So that goes back to the origin. Now we're at pi over 2. We get r of pi over 2 is equal to 3. Because you get cosine of 2 pi, which is just 1. And then multiply that by 3. So that would be up here, given that we plugged in pi over 2. So then it would be, that'd be 5 pi over 8. That would be 3 cosine of 5 pi over 2. And that would be 0. So we go back to the origin again. And you may start to see the pattern here. Our rose curve actually starts to come out a little bit. So now we have theta equals 6 pi over 8, 3 cosine of 4 times 6 pi over 8. We get, what is this? 6 pi over 2. This is cosine of 3 pi. That would be, oh, that would just be negative 3. Sorry, I had a brain fart a little bit. But that'd be around over here. If I can just draw, hopefully. Okay, I'll move over to this side. Theta equals 7 pi over 8. We get 3 cosine of 4 times 7 pi over 8. We get 7 pi over 2. That equals 0. We go back to the origin. And for our final one, pi, we get 3 cosine of 4 pi is equal to 3. And so our function starts, well, hang on, let me just draw this out. So our function starts here and it ends right there. So if you look back at our answer choices, this does actually match 1 and it matches A. So our answer choice for number 2 is A. So we're looking at question 3 now. Question 3 is asking us for what the function r equals 3 over sine theta would look like. Well, this is very simple. This is just y. Well, we can go back to y equals r sine theta. So that pretty much says that y would be a horizontal line. R sine theta would also be a horizontal line. Thus, if you move sine theta over, you get r sine theta is equal to 3. Thus, it is a horizontal line centered at y equals 3. That is the solution to this problem. Find the area between the curves defined by the polar equations r equals theta squared plus 1 and r equals 1 for all of theta between 0 and 1 inclusive. Okay, so let's look at this. And give me a second actually to erase what I had for the previous question. Let's write out our two functions here. We have r2, I'll say r2 is theta squared plus 1, r1 is equal to 1. And we're looking for the area between the function between 0 is less than theta is less than 1. So before we even begin, we have to determine which function is going to be the greater function given the theta value. And I mean, you can see it just from the two equations here. R2 has to be greater than R1 because R2, even when theta is 0, already starts at 1. Because it's theta squared, R2 will only get larger. And you can pretty much see this. If I draw this out for you, this is what the function would look like. This might be your circle, r equals 1. But this would be your graph, r squared equals 1. You can see it just gets larger and larger. I mean, it's like not drawn to scale, but you get the idea. So it would be from probably like, I think, here to here probably. This is the area you're looking for. Doesn't matter. So how do we figure out how to calculate the area of a polar function? Well, just remember that you're pretty much slicing your polar function into small area sectors. So it would be a small sector d theta. You have a small arc length d theta, and you have r as your radius. Sector area, I'll say, just as A, is denoted by 1/2 r squared d theta. Because it's pretty much just r squared times the arc length. So, actually, in fact, this should actually be d theta here. And let me get this keyboard out of the way here. God damn it, what is this? Okay, d theta there. So r squared d theta. That's the area of one small sector. And you're pretty much adding up the area of all of these small sectors, but you're finding the differences in area between the larger and the smaller one. That's what we're trying to find here. So let's set up our integral. It'd be 1/2. We can bring the 1/2 out from 1 to 0. Theta squared plus 1 squared minus 1 squared d theta. And you solve from there. We would get is equal to 1/2. What is this? 0 to 1. Theta fourth plus 2 theta squared plus 1 minus 1 d theta is equal to 1/2 0 to 1 theta fourth plus 2 theta squared d theta, and that would become 1/2 theta fifth over 5 plus theta cubed times 2/3, all between 1 and 0. That would be 1/2 theta, that would just be 1/2 actually, 1/2 1/5 plus 2/3. You don't even need to care about the 0 since it all goes to 0. That would be 1/2 times this giant blob. That would be 3/15 plus 10/15, and when you multiply everything out, you get 13/30 is your answer to this problem.
Welcome back. Today we are going to go over this question 5. The equation of a plane is given by 3x minus 2y plus 13z is equal to 10. Find the value of a such that the vector represented by a, 4, 2 is parallel to the plane. In this case, a should equal, and then we are left to solve the problem. So let me write out the plane here. The plane is 3x minus 2y plus 13z is equal to 10, and our vector is equal to a 4, 2. I want to remind you when we solve this problem that this side of the equation right here is actually represented by a dot product between the normal vector and any arbitrary vector x, y, z. Now this vector, we'll call this vector n, is the most important. This is the vector that sticks outwards perpendicularly to the plane and represents its orientation. In this case, if it represents the orientation and it sticks out perpendicularly, then this vector v that sits on the plane has to be perpendicular to this vector n. Well, then how do we solve this problem? This problem essentially asks us, what is the value of a such that n dot v is equal to 0? Now let's do that. We have 3, negative 2, 13. We have a 4, 2 here. We're going to dot this. You get 3a minus 8 plus 26 is equal to 0. Because let me remind you that the dot product of two perpendicular vectors is 0. 3a is equal to negative 18. A is equal to negative 6. And you can't go back and check this, but for the purposes of this video, I will not. But that is one of the answer choices. That'll be answer choice B. A is equal to negative 6. Hello, everybody. Thank you for joining me. We're going to go over question 6. Find the volume of the parallelepiped where the following three vectors correspond to the three sides of the parallelepiped given by the three vectors shown below. So I'm just going to quickly copy these vectors. We have OA equals 2, 1, 1. We have OB is equal to 0, 0, 1. And we have OC is equal to negative 1, 0, 0. Okay, so I'm going to quickly draw out a diagram here. Let's say I'm on my coordinate axis and I have three vectors. They look like this. Okay. These vectors can form their own sort of parallelogram-ish shape. If I can just draw this out here. So this will look like that. So this will look like that. That would be your parallelogram-ish shape. Okay? So how do we find the volume of this parallelogram using the vectors? Well, the first thing that we have to do is we have to find the base area. The base area can be found by crossing these two vectors. We'll call this vector v2 and v1. Okay? So in this case, we can say that OA is equal to v1 in this case, and we'll call OB to be v2. So to find the area of this base, it would be OA or v1, or actually OA or v1. I'm going to draw it down here, cross OB or v2. Let's do that now. We take out our determinant matrix here for the cross product. We get 2, 1, 1, and we get 0, 0, 1. Now, if you don't remember, what you do is you start by taking this coefficient here and multiplying it by the determinant of this section of the matrix. So in this case, it would be 1, 1, 0, 1 multiplied by I. You do the same thing for j, so it would be, but in this case, you subtract this component of j, so it'd be minus 2, 1, 0, 1. I'm taking from these coefficients here, so that would these form, or these columns here to make 2, 1, 0, 1. That would be j, and then plus, finally, k goes down to here, and it takes 2, 1, 0, 0. Okay, now the determinant of each of these small matrices is found by multiplying these two and subtracting it from these two. So in this case, for I, for example, it would be 1 times 1 minus 0 times 1. And that would be I. So we do the same for all of those. We end up finding that this vector is 1, negative 2, and 0. That would be our area vector of the base of this parallelepiped shape. Now, as you may know from the cross product, the area vector of a cross product on the left side of the screen sticks directly outward, perpendicularly outward from the plane that these vectors form. And if we have a third vector here, we'll call this V3. We may notice that as V3 becomes parallel with either V2 or V1, the volume shrinks to 0. And as V3 approaches perpendicularity with V2 or V1, its volume becomes maximized. So what does that tell us then? That tells us that the volume is maximized when V3 is parallel with A. And this signifies that we should use the dot product to complete the calculation of finding the volume. So volume here would be represented by OC, which is the final vector that we have not used yet, dotted with A. Our OC vector is negative 1, 0, 0. We dot that with 1, negative 2, 0, and we get a dot product of 1. But our work yet is not complete because this signifies that we have a negative volume. However, we are looking for the magnitude of this value. And because magnitude is always positive, the magnitude of the volume that is represented here is just 1. So the correct answer to this problem is 1. Welcome and welcome back. We'll be going over question 7. Find the area of the region bounded by the curves x equals 4 plus 6y squared and x equals 10. So I'm going to quickly write these out. We have x1 is equal to 4 plus 6y squared and x2 is equal to 10. I'm going to quickly draw this out. It'll look something like this. A horizontally right side opening parabola and a vertical line. And we're looking for this area enclosed by both of them. We are not looking for this area or this area because they don't actually have a boundary. They go on for forever. So just this area in here. So what does this tell us then? We are looking for a region in which x1, or the parabola, is less than or equal to x2 for all values of y. Now I've pretty much set up the inequality here. Now it's just down to find the bounds for which this is true. So let's do that. 4 plus 6y squared must be less than or equal to 10. 6y squared must be less than or equal to 6. Y squared must be less than or equal to 1. Y must be less than or equal to plus minus 1. Now we have a plus minus 1 here, which means that we split this plus minus 1 into negative 1 is less than or equal to y is less than or equal to 1. Now this will be the domain for which we will integrate over, or over which we will integrate. So let's do that. We have negative 1 to 1 of 10 minus, in parentheses, 4 plus 6y squared dy. I do 10 first because it is the bigger function in this case. Then we integrate. That would be, well actually, let's simplify this. 1, that would be 6 minus 6y squared dy. Now we integrate. 6y minus 2y cubed from 1 to negative 1. That would be 6, 1 minus 2, 1 minus 6, negative 1, minus 2, negative 1. Yeah, and that would be 4 minus negative 6 plus 2. That would be 4 minus negative 4, which in this case would be 8. So that would be the solution to this problem. The area between these two curves is 8. Hello, thank you for joining me. I hope you are having a good day today. We are going to go over question 8 of MA166 question spring final of 2024. A spherical tank 10 feet in diameter is half full with water with a density of 62.5 pounds per foot cubed. The work required to pump all the water in the tank to the top of the tank is given by the following integral. Let the origin be the center of the tank with the y-axis pointing upward. So I think the hardest part for me was not actually the calculations, it was the wording of the problem. So I'm going to quickly draw out our circle here. I'm going to draw out our axis, x and y. Our tank is going to be half filled with water, so this will be our water. Let's make a distinction here. When they say to the top of the tank, they do not mean this. More so, they mean that there is actually a pump extending out of the top of the tank, and water is rushing through to the top of the tank like this. And we have to calculate how much work has been done to bring the water from its base point down here all the way up to the final point at y equals 5. This second scenario is what we'll be looking at today. So let us begin. When we calculate work, we want to split this problem into infinitely small cylinders, each with their own small volume. I'm going to start by writing out the density, 62.5 pounds per foot cubed. And now we're going to calculate the volume. Let's represent the volume as a cylinder. A very small or very thin cylinder at that. The cylinder has its own radius of r. The cylinder has a height of h. Now, because we are sweeping along the y-axis upward, we can pretty much say that this very small height of h is just equal to our differential, or dy. Now, how do we find the radius? Well, this is where we would use the semicircle function, which would be equal to y equals, well, actually, in this case, because we are integrating with respect to y, it would be this instead. It would be x equals 25 minus y squared, or more generally, r squared minus y squared. We are given that the radius of this circle, or the diameter of the sphere, is 10 feet, which means the radius, the maximum radius, would be 5 feet. 5 squared is equal to 25. This is how we get this function over here. That means that r, in this case, would be equal to the square root of 25 minus y squared. Following the formula of a cylinder, we can calculate that the volume at each of these points would be equal to the density, it would be equal to pi r squared times height, or equal to pi times 25 minus y squared multiplied by dy. That would be the infinitely small volume. Then finally, to reach the mass, or in this case the weight since we're working in pounds, it would be dV, or 62.5 multiplied by pi 25 minus y squared dy. Now, just to clarify something here, we don't actually even need to worry about a gravitational, like the factor of g equals 9.8 in this example, because pounds are already your weight unit. They are not mass, they are weight. So we do not need to include the g. Now we have the weight for this problem. What it comes down to now is finding the total distance that the water or any slice of water might travel to be pumped to the top of the tank. So we're going to come back to this example here. If I have water, obviously, if I have water, the water has to travel this distance of y, and it has to travel this distance of 5 to reach where it's going to go. So its starting point would be all the way down here, and its top point would be at 5. We know that difference in height is equal to h2 minus h1, which means that our difference in height would be 5 minus the y value of our small cylinder of water. This gives us our height value, and now we have everything we need to set up the final integral of work. Work done, in this case, I'll say work is u since w is already taken, would be the integral of 62.5 pi times 25y squared multiplied by 5 minus y dy from -5 to 0. It is from -5 to 0 because that is where our water is located from, or the region between which our water is located from when the problem first starts and before we've even pumped any of the water. This is our final integral. Is there any solution that matches this? There should be. The solution that matches this is solution A. Thank you. Welcome back. We're going to go over question 9. Find a volume of the solid generated by revolving about the y-axis of the region bounded by y equals 0, y equals the function, x equals 1, and x equals 2. So I'm going to write that all out. Y equals 0, y equals 1 over x plus x3, x equals 0, x equals 1, x equals 2, which is essentially saying it's 1, x, 2. So that would look something like this, probably, is the function that we're going after. I think is what's happening. That's just like a very a rough estimation of what the function may look like. But what it looks like does not really matter. What matters is how we solve this. So you may think that we can integrate in terms of y like this, but there are multiple problems. First of all, this function cannot even be separated to be in terms of y. And secondly, if you did it in terms of y, you would end up with two outputs of y for one value of x, which technically means that it is not a function in terms of y, or it's impossible to be a function in terms of y, because it does not pass the horizontal line test. This means that we are down to one more option, which is the shell method. The shell method is essentially that you can split your function into a series of circular shells, each with a very, very thin thickness, or very, very thin, and the very small volume would look like this. It would be 2 pi multiplied by x, and then multiplied by the height, which in this case would just be f of x. So we derive that because this has a radius of x, which means it has a circumference of 2 pi x, and then you multiply that by the height for how high it is, and then you also multiply that by the x for how thick the shell might be, if the shell does in fact have a thickness. And then you essentially do that for an infinite amount of slices between the areas that you want to integrate, which we've established is between x equals 1 and x equals 2. So let's write this out. We have the integral between 1 and 2 of 2 pi x times 1 over x times 1 plus x squared dx. This becomes 2 pi over 1 plus x squared dx. This is actually just 2 pi times arctan of 2, following arctan of x, following our trig identities here. That would be from 2 to 1. Now let's solve this. We get 2 pi arctan 2 minus 2 pi arctan 1. But as you may recall, arctan of 1 is equal to tan of pi over 4, which means that arctan of 1 simplifies down to pi over 4. You get 2 pi arctan 2 minus this blob here, which just becomes pi squared over 2. And thus, you get your solution. which would be A. Welcome and welcome back. Today I bring you good news that I just reached 8K trophies in Clash Royale, so I feel ready to tackle this problem. The graph of f of x is equal to 1 over 4x plus x cubed on the interval 1, 4 and is revolved about the x-axis. Find the right formula that describes the area of the surface generated, and we have 5 options to choose from. So before I even do anything else, I want to make a distinction. We are not looking for volume here. We are looking for surface area. I'm going to circle this and put a check mark and a smiley face next to it. So let's visualize before anything else what we are looking at or for in this problem. I'm going to draw a shape out here. The shape looks something like this. In fact, I'm actually going to make it look like that. So it looks like this. Oh, that's actually not possible. Oh, whatever. But the shape will look like this. This shape will look like that. So the first thing we need to consider is that we are doing revolutions, or we are revolving around. So we have to think about, we might be taking a profile, we might be finding its individual value or something like that, or its individual dimension, and then revolving that around the x-axis. So this problem requires us to consider splitting this shape up into very thin disks or very thin shells and calculating their individual surface areas and then summing all these individual surface areas together to get our final sum. So I'm going to bring this out here. Our functions, or this function's, this little shell surface area, it will maybe look like something like that. Now, before I do anything else, I think it will be better if we could actually flatten this thing into what it actually is, which is just a thin strip that has been sort of like maybe taped together at both of its ends to form the ring that we see on the left side. And then from here, we just solve for the dimensions of this flattened out version, and that gives us our surface area of this specific slice. So let's solve for what this part is. Now this part right here will link to this part down here. And I want us to consider what that might look like. If I have a very fast function, a very rapidly changing function, for each small x that I move, I'll call this delta x, my y value will change by maybe this much. And you'll see this is a very drastic change. But if you look at here, I do delta x here again, my y value does not change that much. So what does this mean then? This means that this side right here is dependent on the speed of the function at any point. And what else is dependent on the speed at any point? The arc length. This value here will be represented as 1 plus df dx squared dx. This part of the value here is the arc length at any point. And this value here is like the very small distance that you move in the x direction. The reason why you need the dx in front is because you're calculating with this formula the arc length at any point, but the arc length at a point doesn't make sense. You need to actually travel a certain distance to calculate an arc length. So I'll transfer that over here. This dimension would be 1 plus df dx squared. Now let's calculate dx. Now let's calculate this dimension here. Well, as you may see, this line here is actually just the circumference of the circle. The circumference of the circle, c, is equal to 2 pi r, where r in this case is just equal to the value of the function at that point. So this side of the line would be equal to 2 pi f of x, which means that our small slice of surface area, delta A, is equal to 2 pi f of x multiplied by 1 plus this squared dx. This results in our final formula, 4 to 1, 2 pi f of x multiplied by the arc length dx. Now, that was the hard part. The easy part is actually finding the arc length value. Our formula for our function here is actually this. I'll bring it down here again so we have reference to it. This, we take the derivative of it, we get negative 1 over 4x squared plus x squared. And then we plug in to solve for the arc length. 1 plus negative 1 over 4x squared plus x squared squared. Expand everything out. 1 plus 1 over 16x fourth minus x squared over 4x squared minus x squared over 4x squared plus x to the fourth. This becomes, parentheses out here, this becomes x to the fourth plus 1 over 16x to the fourth plus 1/2. And it may look impossible to factor this, but if it looks impossible to factor, but you're not done yet, it probably can be factored. And in this case, it's factorable into x squared plus 1 over 4x to the squared, and square that. Now, take the square root, and our final formula for arc length is this. And we already know what f of x is, which means we can assemble this integral. Our final integral would be the integral from 1 to 4 of 2 pi times 1 over 4x plus x cubed over 3 times x squared plus 1 over 4x squared dx. Now, which of these answer choices looks like this? We see that the answer choice corresponding to our result is C. So the answer to this problem is C. Welcome back. Today we will go over question 11. Compute the integral from 0 to pi over 2 of x squared times cosine of x dx. I'll write out the formula, or the integration that we need to do here. And let us begin. So we see the product of two different functions that we think we cannot solve, or we think we cannot integrate together using our regular integration techniques. We immediately think integration by parts. To remind you, integration by parts essentially states that if you have two different functions, u and v, the integral of u dv is equal to uv minus v du. Just as a reminder. Now, you may look at this and you may see tabular method. Tabular method is fine. I will not use tabular method just because I want to represent everything, all of the work. So what is our u function? What is our dv function? Well, our u is always going to be the power function because we can always reduce the power function down to 0 through differentiation, but we cannot do the same thing for something like cosine. So let's do that. U is equal to x squared. dv is equal to cosine of x dx. Always take the derivative of u. du dx is equal to 2x. Always integrate dv. v is equal to sine x. And now we can do our first thing. X squared sine x minus, and our first part integral. We have sine of x times 2x dx. I got this by using this. du dx is equal to 2x. I moved the dx over to the other side. Now we do the same thing again. Our u function is 2x. Our dv function is sine of x dx. So du dx again is 2. I'm going to erase this part here. And our v function is negative cosine of x. Now, let's bring everything down. Minus, put this in brackets, brackets, and then we do 2x, negative 2x cosine of x minus, integrate negative cosine x times 2 dx. And now we see we no longer need integration anymore. we can simplify out the two negatives that we have here, make it a plus, and we solve. X squared sine x plus 2x cosine x, and then this would be minus 2 sine x, all of that between 0 and pi over 2. We plug everything in, we get pi squared over 4 sine of pi over 2 plus 2 times pi over 2 times cosine of pi over 2 minus 2 sine of pi over 2. And then we do the same thing here. 0 squared. So maybe I'll keep it actually. 0 squared sine of 0 plus 2 0 cosine of 0 plus minus 2 sine of 0. So this is pi squared over 4. Cosine of pi over 2 is 0 plus 0 minus 2 times sine of pi over half, or pi over 2, which is 1. And then we have the second part, that's 0, that's 0, that's 0. So we get our final solution here to this equation, or this integral, pi squared over 4 minus 2. Now which solution is that? That would be C. Hello everybody. I hope you're having a good day today as we go through MA 166, this final exam. We are going to go over question 12. Compute the integral from 3 to 4 of 2 over this polynomial shown below. Let's write everything out here. We have this 3 to 4 of 2 over x squared minus 3x plus 2 dx. Okay, we see a polynomial on the bottom. This polynomial cannot be u-subbed. As we may see, it cannot be done with a trig substitution or a trig identity. So what we're left with is we have to see if we can factor it out and perhaps use fractional decomposition. And in fact, we are lucky because we can factor this and we can use partial fractional decomposition. Let me remind you that what that says is essentially any value a over the first term plus b over the second term is equal to this, x minus 1 times x minus 2. You're essentially splitting it up into into the sum of all of its possible remainders. So let's solve. The first thing we do is we multiply everything in here by a factor of x minus 1 times x minus 2, so we can remove all of the denominators here. It just makes everything easier. And we do that on the left side as well. X minus 1 times x minus 2. Then we get a x minus 2 plus b x minus 1 is equal to 2. All we can do is can pretty much sub in x to be equal to one of these values such that that value goes to 0 and we're left with only one constant. I'm going to start with a. A here, we sub in x equals 2 and we get 0. For this one, and we get b times 2 minus 1 is equal to 2. B here would be equal to 2. I'm going to do the same with A. A times 1 minus 2 in this case, since B has 1 minus 1, and then we'll see what that equals. We get negative A is equal to 2, or A is equal to negative 2, and thus we now have all of the constants that we need to solve this integral. So let's reset this thing up. If my thing can stop breaking. All right, integral from 3 to 4. Same thing as last time. Negative 2 over x minus 1. Be very careful about which of these coefficients you associate with which of these terms here, because you may get it wrong, and that will cost you the problem. So it's negative 2 over x minus 1 plus 2 over x minus 2 dx. And as you may see, this is just the sum of two integrable functions corresponding to an integrated function of ln of x. So this would be negative 2 ln of x minus 1 plus 2 ln x minus 2. Throwing that from 3 to 4, from 4 to 3. So that would be negative 2 ln 3 plus 2 ln 2 minus, in parentheses, negative 2 ln 2 plus 2 ln 1. And then this automatically goes to 0 since ln of 1 is 0. We are left with 4 ln 2 minus 2 ln 3 as our solution. Does this equal an answer choice? It does. This equals D. Welcome and welcome back. I hope you're having a good day today as you watch this video. Today we're going to address question 13. Write out the form of the partial fraction decomposition of the function x cubed plus x squared plus 10 over x minus 1 squared times x to the fourth minus 1. So I do have the function already written out. And while this function or this problem may look harrowing at first, it is actually not so bad. We just need to understand what is partial fractional decomposition. So that is just saying we take this blob and we reconstruct it as all of its different remainders. And these remainders are dependent on these specific components like x minus 1, x minus 1 squared, blah, 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 whatever comes out when we actually factor this thing out. The important thing is understanding what the rules are with partial fractional decomposition. The first rule is each of these terms is going to have a solution set whose maximum degree is one less than the denominator's degree. So let's say here, actually I'll write out the denominator first. I have something like x squared plus 1. The maximum degree solution set that I can have for this problem is ax plus b. Now I may not have ax, I may not have b. I could have ax on the top, or I could have b, or I could have both. To include ax plus b is to include all possible solutions, even though you may not use all the terms in the solution. So let's take, for example, I have an x minus 1 on the bottom. The highest degree term that I can have on the top is x0 multiplied by a constant. In this case, this would just be c over x minus 1. And this pattern pretty much continues on. You have to consider every possible solution. So in this case, if I have something like x cubed plus 2x squared plus 1 on the bottom, my maximum solution set on the top would be ax squared plus bx plus c. And the pattern continues on and so forth. However, I want to make a very clear distinction. This rule only applies when your bottom polynomial cannot be factored out any further. What I mean by this is if I have something like x minus 1 squared on the bottom, your top component's solution set will still only be x to the 0 times c, because you are not considering this exponent, you are considering this exponent right here. In this case, because the exponent attached to x is still 1, your solution set is only to the x to the 0 degree. Now, why is this? Let's say, for example, I didn't pretty much chicken scratch all over my thing. So I have this, right? And I might have like x plus 2 or something. I don't know, that's like a placeholder. I can split this up into x plus 2 over x minus 1 times x minus 1, in which case I can further decompose this into a x minus 1 plus b x minus 1, which is just a plus b over x minus 1, which could just be equal to c over x minus 1. So there. Let us continue on. What's the second rule then? The second rule is that if I have something like x minus 1 to the fourth, and I have some sort of function on top of this, I need to decompose into every possible thing. So I would have x minus 1 to the fourth plus b over x minus 1 to the third plus c over x minus 1 to the second plus d over x minus 1 to the 1. And then I wouldn't go any further than that because, I wouldn't go any further. So we just do this also to pretty much consider every possible solution that there might be, or every possible term that there might be when we reconstruct this. Obviously, this might not contain everything, all of these terms, but it's for security. Now, knowing these two things, we can finally decompose this and reconstruct it. Well, I'm going to bring our function down to here, and it'll look like this again. X minus 1 squared times x to the fourth minus 1. What they're looking for first is you can factor that out into a difference of squares, I think is what it's called. This would be x squared minus 1 times x squared plus 1. You can further factor this out into x cubed plus x squared plus 10, x minus 1 squared. You can further factor this out into x minus 1 and x plus 1, and you cannot factor x squared plus 1 anymore. So now we pretty much are at our lowest state here. We have x minus 1 cubed on the bottom times x plus 1 times x squared plus 1. Now it just comes to reconstructing all of these terms together. Now using the two rules that I have established above, we can say the first term would be x minus 1 cubed under a plus b x minus 1 squared plus c over x minus 1 plus d over x plus 1, and then plus ex plus f over x squared plus 1. If you do not know how I was able to reconstruct each of these terms, there is further resources on the internet, so I would recommend looking that up. But this would be the final reconstruction or the final general solution to this problem. And which one does this match? This matches solution A. So A is the correct answer choice for this problem. Welcome and welcome back. I hope you are doing well at the time of watching this video. We are going to go over question 14. Evaluate the improper integral, the integral of 0 to 2 of x ln x dx. So I have the integral written now right here. And the first thing we should ask is, what is the value at which this function is undefined, this integral is undefined? And immediately we can see it's 0. ln of 0 is undefined. So what do? We replace that with a new variable, we'll call this a, and take the limit instead. So it'll be the limit as a approaches 0 from the right side only, the integral from a to 2 of x ln x dx, and this problem simply becomes integration by parts. So we are going to use u as ln of x simply because taking the integral of ln of x would require unnecessary integration by parts, and I also had a battery, so let's finish this up. Du dx is equal to 1 over x. Our dv is equal to x dx. V is equal to x squared over 2. So let's write this out. X squared over 2 times ln of x minus, and then our v du. So this would be x squared over 2 times 1 over x dx from the same bounds. I'll just write it from a to 2 again. I will not include the limit since I don't have the space here. Ln of x minus, so the integral, x's cancel out, dx, this becomes x squared over 2 ln x minus x squared over 4. And then that's from 2 to a, and this is all under the limit as a approaches 0 from the right side. Let's do this now. So we have, the first thing that we have is 2 squared over 2 ln of 2 minus 2 squared over 4 minus, in parentheses, a squared over 2 ln of a minus a squared over 4. Now, nothing here is really problematic except for this term right here. Now, this relies on us to use a L'Hopital's method here. If we have our function f of x is equal to x squared over 2 times ln of x, we can actually rewrite this to be f of x is equal to g of x over h of x is ln of x over 2 over x squared. And then if we take the limit as both of these approach a 0, x, sorry, I don't even know why I blanked for a second. So this would be ln of x over 2 over x squared. Both of them approach an indeterminate form of infinity or negative infinity in this case. So then we can take the L'Hopital. We would do 1 over, okay, hang on. Actually, I'm going to write the entire thing. So this would be d dx of ln of x all over d dx of 2 over x squared. And that would be 1 over x over 4 over x cubed net negative. And then we take that same limit as x approaches 0 from the right side, and we can pretty much cancel everything out at this point. So we have 1 over x times x cubed over 4. The limit as x approaches 0 to the right, we get x squared over 4. X approaches 0, 0 over 4. This approaches 0. So as if determined from L'Hopital, this term here will go to 0. That term there will go to 0. Eventually, we are just left with this. 2 ln 2 minus 1. This is the solution to our integral, which would be answer D. Hello everybody, thank you for joining me. We're going to go over question 15. Calculate the integral from 0 to pi over 2 of sine squared theta, cosine cubed theta, d theta. We are given 5 possible answer choices. To begin, I am going to draw the integral out in whiteboard first, and we will solve from there. So this is sine squared theta times cosine cubed theta d theta. Now let's begin. You may be thinking, as I did when I first saw this problem, that a u sub is the best course of action. However, as you may notice, a u sub is not possible because this exponent here would have to be 1 for the u sub to be valid. Since when you do when you take the derivative of cosine of theta, you do not get sine squared of theta, you just get negative sine theta. So u sub is not valid in this problem. Rather, we need to see, well, we cannot work with cosine cubed theta. We can, however, work with cosine squared theta. So we have to see how we can pull cosine squared theta out of this problem and work with it that way. Well, that's just very simple. It just comes down to pretty much splitting that cosine cubed theta into cosine squared theta and cosine theta. So let's do that right now. And that'll look like this. Recall our trigonometric identity where sine squared theta plus cosine squared theta is equal to 1. That means that cosine squared theta is equal to 1 minus sine squared theta. We'll sub that in. 0 over to pi over 2 of sine squared theta, and it is 1 minus sine squared theta, cosine theta, d theta. And now a u sub is actually possible. In this case, u would be equal to sine theta, du over d theta is equal to cosine theta, and then you simply rearrange it algebraically where you get it in terms of du, and you're trying to sub in for d theta. So you get 1 over cosine of theta for that. Then it becomes d theta is equal to du over cosine theta. And then we can sub everything back in. So now we have 0 to pi over 2, or actually, in this case, it would be u0 to u pi over 2, because we are actually now in a new base. We've changed variables from theta to u, so our bounds are now different. But I'll just leave u0 and u of pi over 2 as placeholders. This would become u squared 1 minus u squared, and then it would be du over cosine theta plus a cosine theta right here from before. However, these simply cancel out, and what we're left with is 0 to 1 of u squared 1 minus u squared du. this integral becomes very simple. This just turns into power expansion, 0 to 1 du. You take the integral u cubed over 3 minus u to the 5th over 5 between 1 and 0. This turns into 1/3 minus 1/5. You combine the fractions with a common denominator, you get 5/15 minus 3/15. Your final solution is 2/15, which means your answer choice to this problem would be D. Welcome and welcome back. I hope you're having a good day. Let's go over question 16. Compute the integral from 0 to 3, 0 to pi over 3 of tan cubed secant cubed x dx. This one is actually pretty tough to spot. So let's go over it. 0 to pi over 3 of tan cubed x secant cubed x dx. The first thing that we want to do is we want to rewrite them in terms of sine and cosine. So this becomes sine cubed x, cosine cubed x on the bottom. Secant cubed becomes 1 over cosine cubed x on the bottom, dx. And sine cubed x cosine 6x dx. Your first instinct might be to do a u sub here, but there was one more thing we need to do before we can actually u sub. Let us change this sine cubed into a sine squared x cosine and then sine x over cosine 6x dx. This allows us to use a trigonometric identity where sine squared of x is equal to 1 minus cosine squared x sine x, and then all of that over 6 cosine to the 6th x dx. And I'll just leave the bounds as a and b for now. And now we can perform a u sub. Let u equal cosine of x. Let du dx equal negative sine x. And then from there, you solve algebraically for dx. And then you sub that back in. You get u of 0 to u of pi over 3. Reminder that we cannot directly import our bounds from before because we have actually changed variables. We have essentially changed bases. So we have to work in the new base of u. We get 1 minus u squared times sine of x over u to the 6 times negative sine of x du. Oh, sorry. This would actually be du over negative sine of x. These cancel, and then you pretty much can bring the negative sign into the 1 minus u squared, such that it becomes u squared minus 1 instead over u6 du. This fraction can be split up into u squared over u6 minus 1 over u6 du. This becomes 1/2, 1 over u4 minus 1 over u6 du. This becomes, okay, so this would become negative 1 over 3u cubed minus plus 1 over 5u to the 5th. All of that between 1/2 and 1. So we sub that in. We have 1 to the 5 times 1/2 to the 5th minus 1 over 3 times this to the 3rd, and then minus, in parentheses, 1 over 5 minus 1/3. What an equation to solve. So we have 1, we actually have 31 over 5 32nds minus 1 over 3/8 minus, again, the same thing as before. I'll just keep bringing it down. Reduce 32 over 5ths minus 8 over 3 minus 1/5 plus 1/3. So this would become 31/5 minus 7/3. We have to do a common denominator now. We would get, what is this, 93 over 15ths minus 35 over 15ths. That results in our final solution of 58 over 15ths as the solution to this integral. Which one is that? Welcome and welcome back. I hope you're having a good day today. You may have noticed that I changed microphone setups, and additionally, I have moved the question directly into the whiteboard. I have done this for this question just because we need to visualize every single one of the answer choices for this question to succeed. Now let's begin with looking at the question. For the integral, I is equal to the integral of 1 over 4 x to the 4th times, in quantity, the square root of x squared minus 4 dx. Choose the right trigonometric substitution and find the resulting integral, and we are given 5 answer choices. Now, this may look harrowing at first. However, there is one thing that we should consider before we do anything else. How do we get rid of the square root? Because there is actually an identity that works here. The identity is tan squared of theta is equal to secant squared of theta minus 1. And you can see here, this is pretty much just x squared minus 1, or actually just x squared minus a. Well, actually, it'd be more like a x squared minus 1. So we can actually use secant squared to reduce down or simplify this square root that we have in the function currently, which means that for that to be possible, our x function cannot be tangent, it cannot be sine, it has to be some form of secant theta. So that means we can eliminate answers A, B, and E, and all we're left with are answers C and D. So let's begin with answer C. Or actually, let's just begin with the function x equals 2 secant theta. As noted by the question, we will have to do a change of variables from x into theta. Now, how do we do that? Well, we have to see how does the function x change with respect to theta, which literally is just the derivative. So we take the derivative dx d theta is equal to 2 secant theta tan theta, following derivative rules for trigonometric functions, and then dx obviously just becomes 2 secant theta tan theta d theta. And now all that's left to do is plug everything in. Our integral here turns into 2 secant theta tan theta d theta at the end over 16th secant to the 4th theta. In square root, we have 4 secant squared theta minus 4. And you may already see how we can get rid of the square root. I'll bring this over to the right side. First of all, we can cancel out. This becomes 3. This turns to nothing. This becomes 1 over 8. And we're left with 1 over 8 times tan theta over secant cubed theta times square root of 4 times in quantity secant squared minus 1. And that is where our trigonometric identity comes forth. We bring the 1/8 out. We are left with tan theta at the top. We are left with secant cubed theta at the bottom, multiplied by 2 tan theta after taking the square root of whatever was in there. And I'll quickly show how you do that. This becomes 4 tan squared theta. By subbing in the trigonometric identity, that just becomes 2 tan theta. Just for quick reference. So we can cancel out tan thetas here. We can bring the 2 out with the 1/8, and our final form, or our second to final form, would be 1/16 times the integral of 1 over secant cubed theta d theta, which inevitably just becomes one of our answer choices, 1/16 times the integral of cosine cubed theta d theta. Now, which of these answer choices does this look similar to? And we see that this actually perfectly matches answer choice C. Welcome and welcome back, everybody. Thank you for joining me today as we solve question 18 of this exam. I hope you're having a good day today as you watch this video. And before we begin, I want to start off with a little update. Today was the first day that I tried carnitas at Chipotle because everything else was out since I went 20 minutes before closing. And I enjoyed it quite a bit actually, so I'm pleasantly surprised. Next on my list will be a burrito, since I've never actually had a burrito from Chipotle. Now, let's start off this integral with a high note. Our integral is shown below, or shown on the page. The integral of dt over t squared minus 6t plus 13 quantity square roots. This problem looks impossible at first, but there is a clever thing that we can do here, and it is not u sub. In fact, it is completing the square. Completing the square says that if I have a polynomial, in this case, I'll just say that the constant for x squared is equal to 1, x squared plus bx plus c. I can turn that into a combination or a sum of both a perfect square polynomial and a constant out in front, which would be equal to x minus x plus b over 2 squared, and then plus another constant k. Now, we can apply the same principle to this problem over here, since it pretty much is the exact same thing. T squared minus 6t plus 13 turns into t minus 3 squared, and then plus some constant out in front. I'll call it c. Now, why do we need this constant out in front? Well, if we expand out this polynomial, t squared minus 6t plus 9 plus c, when in fact, your constant value should actually be equal to 13. This is pretty simple algebra. 9 plus c must be equal to 13, therefore c must be equal to 4. And now we can rewrite our integral to include this completed square polynomial. In parentheses, t minus 3 squared plus 4 on the bottom. This equation, or this integral, still looks impossible to solve, but there is a clever trigonometric identity we can use and a clever trigonometric substitution. Recall that secant squared theta is equal to tangent squared theta plus 1. I would keep this identity in mind. I would also keep in mind that tan squared theta, on the contrary, would be equal to secant squared theta minus 1. These are both very important identities that you'll need to remember. They're not as simple as something like sine squared x plus cosine squared x equals 1, but they're still very, very important for Calc 2. Now, using these, how can we solve this problem? Well, we can already identify that this thing here, t minus 3 squared plus 4, is kind of just the same thing as tan squared theta plus 1, the only difference being that, well, we have t minus 3 as our tan instead of tan, and we have 4 instead of 1. So we can convert this equation into the form of tan squared theta plus 1. How do we go about doing that, though? Well, we already know off the bat that t minus 3 has to be equal to tan theta, since they're both sitting in the same spot as the function square. We also know that if we have the 4 out in front, that means our function, once it's been squared, has to have a coefficient of 4 out in front of it. Let me demonstrate. Let's say, actually, I'll just even use this example here. We have a tan theta squared, and then plus 4. That becomes a squared, I'll write it here, a squared tan squared theta plus 4 would be equal to secant squared theta. Now, we would be able to factor out a 4 out of this equation and effectively turn it into the identity that we see up in the top right if a squared is equal to 4. If a squared has to be equal to 4, then what does a have to be equal to? It would have to be equal to 2 in this example. Our final function would be turning t equals 3, t minus 3, into 2 tan of theta. We are converting from a basis of t into a base of theta instead. So how do we complete this transfer? Well, let's move our 3 to the other side. And then we have to change the differential here from dt into d theta. How do we go about doing that? We take the derivative dt d theta is equal to 2 secant squared theta, and then it just becomes dt equals 2 secant squared theta d theta. Now, let us take this information and use it to solve the integral shown above. We have our original integral here, t squared minus 6t plus, actually, I'll write it in complete square format, t minus 3 squared plus 4. This becomes 2 secant squared theta d theta over 4 tan squared theta plus 4. You can pull out the 4 out of the square roots. It becomes 2, and then, of course, tan squared theta plus 1. But as we just discussed, that identity is equal to secant squared, which means that we can effectively make the bottom just 2 secant theta on the bottom, d theta. Thetas cancel out, 2's cancel out. All we're left with is the integral of secant theta d theta. Now, there is a way to obviously derive the integral for this formula, or derive the solution to this integral, but for the purposes of the exam, it's best to memorize this integral. The integral of secant theta d theta is equal to the natural log of the absolute value of tangent theta plus secant theta. Boom. Let's recall, we know that tan theta, or 2 tan theta, would be equal to t minus 3. Let's also recall that tan squared theta plus 1 would be equal to secant squared theta. Solving for tan theta and plugging it back into this integral here, plus Carlotta constant of integration out front, solving for tan theta is very simple. With tan theta just becomes t minus 3 over 2. That is our tan theta component. Secant squared is a little bit different though, but it's not much harder. Secant theta is equal to the square root of tan squared theta plus 1. We already know what tan squared theta is. Tan squared theta would be taking this solution here and simply squaring it, which means that secant theta out in front would be equal to the square root of t minus 3 over 2 quantity squared and then plus 1. Secant squared theta, or secant theta, would then be equal to t minus 3 squared on top over 4, and then we can turn the 1 into 4 over 4, and now we can pretty much plug everything in. This integral, we substitute in tan theta and secant theta, we get the integral of this function is equal to natural log of t minus 3 over 2, and then plus the square roots, the square root of t minus 3 squared plus 4 over 4, and then you simply bring the square root out of the denominator by turning the square root of 4 into 2, and you're left with your final solution, the natural log of t minus 3 over 2 plus square root of t minus 3 squared plus 4 over 2 plus c out in front. Now, which of these solutions or the answer choices best corresponds to our solution? That would be answer choice A. Welcome and welcome back. Thank you for joining me today. Let us go over question 19. Which of these following 3 series converges or converge absolutely? And we're given 3 different series to look at. Let's look at the first series. This is to say that if you remove the alternator in front and we're just left with the series of 1 over ln of k, would the series converge? And the best way to do this one is by using comparison. Let's compare this to a similar series, and we know that the natural log of x has a relatively similar shape to that of the square root of x. Well, we know that 1 over square root of x, that series diverges. So we have to determine whether or not the square root of x is greater than the natural log of x. If the square root of x is greater than the natural log of x, that means that all the terms 1 over the square root of x must be greater, or they must be less than the natural log of x, 1 over the natural log of x. In which case, if we know that the 1 over square root of x diverges, then we know also that 1 over ln of x must also diverge. Now, you can look for the proof yourself, or the derivation yourself. I'm not going to go over the derivation in the interest of time, since we do have 2 other series to go over. But just know that for every value of x, the square root of x is greater than the natural log of x. And thus, by reasoning, 1 over square root of x must be less than 1 over ln of x. And this diverges, which means that since each term in 1 over ln of x is greater, this has to diverge also, which means that 1 does not converge at all. Let's look at series 2. Series 2 is the sum of 1 over k to the 5/4 plus k. Now we already know right off the bat that this series converges because we have the 5/4 in the exponent. We can use the p-series rule where if p is greater than 1, then the series converges. But if p is less than or equal to 1, the series diverges. In this case, p is equal to 5 over 4, which means that the series converges, absolutely. So 2 gets a check mark from us. Let's look at series 3. We have n over 2 of n. The 2 of n, the 2 to the n screams at us, do the ratio test, do the ratio test. And so we shall do the Horatio test. N plus 1 over 2n plus 1 over n over 2n, 2 to the n, my apologies, all under the absolute value, the limit as n approaches infinity. Well, let's do this. We have n plus 1 over 2n times 2 times 2n over n. And also the limit as n approaches infinity. This cancels, that cancels. As n approaches infinity, this value of 1 becomes very insignificant. So we can pretty much eliminate that. Then n cancels with n, and we are left with 1/2 to be the ratio between each succeeding term and its previous. Because the ratio is less than 1, we know that the series must converge absolutely, and thus this series also gets a check mark from us. And thus, we have our answer to this problem, C, 2 and 3 only. Welcome and welcome back. I hope you're having a good day as you watch this video and go over question 20 with me on this final exam for Calc 2. Now let's begin. The interval of convergence for the power series, the series from n equals 1 to infinity of the terms given is, and then we're given 5 different options. So before I even begin, let me transfer over this series here. From n equals 1 to infinity, we have 3n times x minus 1 to the n, and then all of that, I believe it was over what? It was over just n. So we have our series here. Now, interval of convergence is screaming at us, ratio test, in which case we will gladly oblige. Oh, sir, ratio test. Let us do this. The limit as n approaches infinity of 3 to the n plus 1 times x minus 1 to the n plus 1 over n plus 1 over, all of this actually, over 3 to the n times x minus 1 to the n over n. All right, let's do this. So we have 3n times 3 times x minus 1 to the n multiplied by x minus 1, and then over n plus 1, multiply that by n on the top. Since we're dividing it, we have to reciprocate it around, x minus 1 to the n on the bottom. All right, a few things here cancel out. That, this. As n grows to really, really big numbers, the value of 1 becomes insignificant. Thus, 1 is canceled. That cancels. And we are left with this as our final ratio solution. Now, We know that for the ratio test to produce a convergent result, the ratio itself has to be less than 1. It can't be less than or equal to 1. It has to be less than 1. So we have no more terms n in here, so the limit is insignificant now. And all we're left with is just to solve for this absolute value inequality. The way we solve for that is essentially saying -1 would be less than 3, would be less than x minus 1, would be less than 1. We have two equations here. 3x minus 1 would be less than -1, and 3x minus 1 would be less than 1. So we have x minus 1 would be less than -2, and then this would become, would be less than -1/3. X would be less than 2/3, positive 2/3. And then for this equation, it would be, or actually in this case, it would be greater than. The inequality would be greater than because -1 is your lower bound. Now let's do the same for here. X minus 1 must be less than 1/3. X must be less than 4/3. So these are our two bounds here. Now the last thing we need to do is we need to check the endpoints themselves to see whether or not the series converges at the endpoints shown. We're going to test, I'm going to bring the series down here so we have a recollection of what the series is. It's this, n, and this would be n. Okay, so we have to plug our x in for either 2/3 or 4/3, and we see which of these produces a convergent series. So we'll start with 2/3. We have 3 to the n multiplied by -1/3 to the n over n. This reduces down to -1 n over n, and that is a series. And we know by the alternating series test that each of these values pretty much reduces to 0 because we're alternating between 1 and -1 on the numerator, but our denominator grows infinitely large. Thus, the series converges at 2/3. Now, does a series converge at 4/3? Let us find out. You're left with this, and then over n again, and this would be 1 to the n over n equals this. And we know this is the harmonic series. The harmonic series follows the p-series rule, where if p is less than or equal to 1, then the series diverges. In this case, p here is equal to 1, and therefore this series must diverge. Thus, it is not valid and does not converge when x is actually equal to 4/3. And thus, we have our final interval of convergence, close bracket, inclusive 2/3 to 4/3, open parentheses, exclusive. Now, which of these answer choices represents this solution? That would be choice D. Hello, welcome, and welcome back. Today, we're going to go over question 21, compute the value of the given series. And we are given a series. We are also given a hint. The question is quite kind. Start from the power series of f of x equals 1 over 1 minus x. What is f prime of x, and how does it compare to the series given above? Let's write both of these series down. We'll say s here is equal to the series they gave us, k equals 0 all the way up to infinity, and this is k plus 1 over 5 to the k. You're also given that f of x equals 1 over 1 minus x, and is the standard power series, and also relates to series s in some capacity. So the first thing that we do is we do what the problem says. What is f prime of x? Actually, before we even do that, let's write out what this series looks like. We'll do that here. The series would be essentially a geometric series where a equals 1 and r equals x. So that would be x to the n, where n starts at 0 and n goes to infinity, which would equal 1 plus x squared plus x cubed plus dot 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 plus x to the n. Now, let's take the derivative of this. F prime of x is equal to 1 over 1 minus x squared. The chain rule says that the negative x is brought out, or the negative 1 from the negative x is brought out, and it cancels out the negative that would usually be there. The resulting series would be the derivative of pretty much every term within the series. Starting from the power rule, that would be n to the x, or n times x to the n minus 1, which would be equal to the derivative of that would be 0. The derivative of this, that would be 1 plus 2x plus 3x squared plus dot 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 plus nx to the n minus 1. Now let's look at what this series looks like. The series is k equals O, or k starts at 0 and goes to infinity, of this. Here, 5k. We're going to put in the first term. That would be 1 on the bottom, and that would be 1 on the top. That would be 1. And then plus 5 on the bottom, and then 2 on the top, 2/5. And then it would be plus, let's see, I think it's 3/25. And then so on and so forth. Now, if you have not seen the pattern yet, these two series are actually just off by a factor of x. And we need to determine what x might look like. In fact, I'll even put them side by side for you to see. It's equal to 1 plus 2x plus 3x squared plus dot 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 plus n times x to the n minus 1. As you can see, this is off by literally a factor of 1/5. In this case, this is just equal to 2 times 1/5, as should this be equal to 2 times 1/5. Which means that if it's 2 times 1/5, and that would be equal to 2x, then algebra wizardry, x equals 1 to the 5th by solving for x. And then we can plug it pretty much into f prime of x to determine the full sum of this series, since the series representing f prime of x and this series we see on the left equal to s are equal. So let's do that for our final step. F prime of 1/5 is equal to 1 over 1 minus 1/5 squared equals 1 over, what is that, 4/5 squared equals 1 over 16/25, which then becomes 25 over 16. That would be the sum of this series S. Is that an answer choice here? Let us see. Yes, that would be answer B. Hello, thank you for joining me today. We're going to go over question 22. Choose the right formulas to compute the volume of the solid obtained from rotating about the line x equals 2, the region bounded by y equals e to the x, y equals 2, and x equals 0. And we're given two calculations I have to make, the washer method and the shell method. So the reason why I did not include the answer choices shown below is because in the original exam copy, there is actually no correct answer choice, even though it might say one. This is already adjusted for in boiler exams, but for the purposes of this video, we will just solve without comparing any answer choices. Let's look at the washer method first. And before I do anything, I'm going to draw out our shape. We're first bounded by x equals 0. We're bounded by y equals 2. And we're revolving around x equals 2. Our function would look something maybe a little bit like that. And we're revolving that around the y-axis. Now let's do that. Because we are revolving, not around the y-axis, we're revolving around x equals 2. Obviously, because we're revolving around a vertical axis, our washers need to run horizontally and parallel to the x-axis. This means that we have to convert our function y equals e to the x to be a function x in terms of y. It's very easy. This just becomes ln of y is equal to ln of e to the x. This becomes ln of y is equal to x. And now we can begin. With these types of problems, we obviously need to find both an outer radius, I'll call this r outer, this will become r2, and an inner radius. I'll call this r inner, which becomes r1. What's the outer radius for this problem? Well, as you may notice, no matter what our y value is, our outer radius is always just the distance, the horizontal distance from x equals 0 to x equals 2, which means that our outer radius, r2, is just equal to 2. but our inner radius is a little bit different because it is dependent on ln of y. We are looking for this total distance right here, which would be represented as starting from x equals 2 and going all the way until ln of y. So kind of be like taking the full radius, but then subtracting it by ln of y because it's being cut short by the function itself. So this would be the inner radius, and r1 here would be equal to 2 minus ln of y. We know that for any washer or for any cylindrical shape, if we have a cylindrical shape like this, there has to be a height. The height here is dy because that's the axis along which we're integrating, and the volume for a washer would be pi r2 squared minus pi, dy minus pi r1 squared dy, and then the volume in total would just be integrating between bounds 1 and 2 of each washer shell. In this case, it would be V total done by washers would be from y1 to y2 of pi times r2, which would be 2 squared minus, in parentheses, 2 minus ln of y squared dy. Now the last thing we need to do is find the bounds. Look at the function over here. We're starting from this point here, and we're ending at this point here. So we are already given, actually, our second y bound, which is just y is equal to 2, but we need to find this one right here. And to reach this point happens when x equals 0, so we just need to plug in x equals 0 into our original function. We can do it either way. Y of 0 is equal to e to the 0, which is equal to 1, or x is equal to, or actually 0 is equal to ln of y. ln of 1 is equal to 0, which means that y is equal to 1. So our two bounds for this problem would be 1 and 2 if done by the washer method. Let's take a look at the shell method. I'm going to redraw out the diagram. It'll look something like this, revolved around x equals 2. Well, the shell method states that we can start at our axis of rotation and we can pretty much fan outwards and calculate the total volume in terms of very thin spherical shells that look, and this would be like your radius from, or like your distance from your starting axis of rotation, which would also be the radius of the shell. And this would be the total height of the shell. You would have a very small thickness here. But I think it's better if we look at this as a flattened out sheet of paper. So imagine this shell to be rolled up like a rolled up sheet of paper, but we're going to flatten out that sheet of paper and turn it into a very small rectangular prism instead. The width of this rectangular prism would be equal to the circumference of the shell. C is equal to 2 pi r, but in this case, our radius is equal to delta x, as shown there. This side would be equal to the height of the shell, but the height of the shell, we're going to say, is f of x at each point x. And finally, the thickness of the shell will be represented as our integrator or differential dx. And that would give us the resulting volume of each shell, which would be v shell is equal to 2 pi delta x multiplied by f of x multiplied by dx. Now we have to find what are delta x and f of x at each point, because as we're going to see in a minute, f of x is not simply equal to e to the x. It's equal to a combination of two functions. Okay, so let's start with finding delta x. We start at x equals 2 and we fan outwards left to calculate everything, which means that delta x on the right side, delta x is equal to x final minus x initial. Our x final would just be our arbitrary x input, and then our initial value would be x equals 2. So this would be equal to delta x, and our function f of x here, as I said, is different because if you look at the diagram, we have another case where we have a big minus a small to calculate our real value here. So our big value, as you may see, is just the distance between y equals 2 and y equals 0. So our big height, we'll call this h big, is equal to 2. But our smaller height here is dependent on e to the x. In fact, it is actually just e to the x. So our smaller height, h small, would be equal to e to the x. And these two, the difference between h big and h small, would equal 2 minus e to the x, and that would actually be our function here. So f of x, for our purposes, is equal to 2 minus e to the x. This is also equal to our height of the shell, or each shell. And now we need to calculate our bounds. We are starting from 2, and we're going all the way up to, well, actually, no, we're not starting from x equals 2. We are starting from x equals whatever this value is and going to x equals 0. So we need to calculate what this value is, and it's actually quite simple. This value here is equal to y equals 2. We just need to figure out what x input results in e to the x equal to 2. That would be y equals e to the x on the right side. 2 is equal to e to the x. Take the natural log of both sides. X is equal to ln of 2. So we would start with ln of 2 on our lower, and we would go to 0 for our upper. So let's write that out. The volume total would be equal to the integral of each, or the sum of each shell, which would be equal to, from ln of 2 to 0, this would be 2 pi x minus 2 multiplied by 2 minus e to the x dx. However, as you may see from the problem set, this is not any of the answer choices that are listed. There's a little bit of bound shifting that we need to do. First of all, we know that the integral from a to b is equal to negative the integral from b to a. We change the integral bounds here from 0 to ln over 2. This becomes negative 2 pi x minus 2 times 2 minus e to the x dx. But as you may see, you can put the integral sign, you can put the negative sign into x minus 2 to turn it into our final form, 0 to ln of 2 times 2 pi times 2 minus x multiplied by 2 minus e to the x dx. And that would be the volume done by shells. Welcome and welcome back. I hope you're having a good day as you watch this video. If you hear a bit of background noise, that is because I'm sitting next to, or sitting in a room with a fan, and I cannot turn the fan off because it required for the room. So I apologize. But let us go over question 23. The alternating series test shows that the series below converges to a finite value s. So, set the partial series, the sum from k equals 1 to capital N of negative 1 to the k times 1 over square root of 5k. Find the smallest n using the estimation theorem for alternating series such that we can conclude that the error here is less than 1 over 10 squared. Let us begin with what exactly is the alternating series estimation theorem. That is all to say that the error here, which is equal to s minus s of n, is only as large as the next term in the series, or the first term that we did not include in our partial series. Now, how can we derive this? I'm just going to show you very quickly. Let's say that our s here represents the full series to infinity, and s of n represents a partial series up until the nth term. And each of these series terms is represented by a of small n. we'll say that. Or a of big N, depending on what we're looking at. We know that because it is an alternating series, that the values, if the series converges, have to get smaller for each new term introduced. So a of n plus 1 must be less than a of n. And with this, we can begin showing why the alternating series estimation theorem works. Let's say that epsilon is equal to the absolute value of s minus Sn, as we've shown above. This means that it would be first the full series from a1 minus a2 plus a3 minus a4 plus dot 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 plus a of n capital minus 1 minus a of n itself. Now, I want to make a distinction that the n that we see here is not the same n that we see here. This is just a substitute variable that I'm using, and we assume that n in this derivation goes to infinity since it is the full series. We subtract that from the partial series a of 1 minus a of 2 plus a of 3 minus a of 4 plus dot 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 all the way up until a of lowercase n minus 1 minus a of lowercase n itself. And in this case, the lowercase n only approaches the last term in the partial series. We'll just call that like k. This is the last term that we're going to within our partial series. We expand everything out, we simplify, and we find that this all cancel out. And all we're left with is a of lowercase n plus 1 minus a of lowercase n plus 2, and so on, so forth, dot dot dot, up until a of n plus minus 1, a of capital N minus 1, minus a of capital N itself. Now, how do we reach this? Well, when we cancel everything out, this cancels everything out up until a of n, which means that the next term that would be fair game in our derivation is a of n plus 1, and this would all be equal to the error epsilon. We have determined from our previous assumption that a of n plus 2 in this example must be less than a of n plus 1, which means that a of n plus 1 of anything must be less than a to the n. Thus, we can conclude that everything after a of n plus 1 must be less than a of n plus 1 itself, which means that we can guarantee that the error must be less than a of n plus 1 or the next omitted term. So all we have to do for this problem is solve for the k value at which this would be true. Let's do that. So we have 1 over the square root of 5k plus 1. We include the plus 1 because we are looking for the next term, or the first omitted one in the series, is less than 1 over 10 squared. We are going to bring everything up, so that way we're not working with 1 over everything, we're working with everything itself. This becomes 5k plus 1. Because we flipped everything, this should become a positive sign instead, and that's equal to 10 squared on the top. Take the square at both sides. You get 5k plus 1 is greater than 10,000. You get, divide this out, divide this by 5. K plus 1 must be greater than 2,000, and k must be greater than 1999 to guarantee what we're looking for. Now, which one is the one that is greater than 1999? That would be 2,000. We don't do 2002 because 2,000 is the first one that meets the requirements. So thus, answer C is the correct choice here. Hello, welcome and welcome back. Thank you for joining me today. Let us go over question 24 of this problem set. In the Taylor series of f of x equals 1 over x centered at a equals 2, the coefficient of this term, x minus 2, quantity to the fourth, is equal to, and we are given 5 options to choose from. Let me transfer all this information in here. The function in question is 1 over x, and we are centering this around a equals 2. So it's no longer a Maclaurin series because now our center of series is 2. It's non-zero. So what will we do? Well, we know that the term x minus 2 to the fourth represents the fourth term in the Taylor series if we have something along the lines of like f prime of 0, or actually this would be f of 0 plus f prime of 0, or actually f of 2 in this case, so it'd be f of 2, times plus f prime of 2, x minus 2, plus f double prime of 2 over 2 factorial in this case, x minus 2 squared, and then plus f triple prime, we'll call that jerk, quite a butt head right there, minus 2 cubed, and then so on and so forth. And actually, conveniently enough, the next term of this series would be f to the fourth over 2 over 4 squared times x minus 2 to the fourth. And we're looking for the coefficient out front of that term, which would be this. So what we need to do is we need to take the fourth derivative of the function f of x equals 1 over x. And we need to plug in 2 at that value and solve. So let's do that. F prime of x is equal to negative 1 over x squared. F double prime of x is equal to 1, or this would be equal to 2 over x cubed. F triple prime of x is equal to negative 6 over x to the fourth. And then finally, f quadruple prime of x is equal to 24x to the fifth. All right, so we plug in at this value. We're looking to plug in the value 2, and that would be 24 over 32. That would give us a value of 6 over 8, or 3 over 4. But in fact, we could probably just leave this actually as 24 over 32, and you'll see why in just a minute. So we plug in after the f of the fourth derivative at the point 2. That would give us 24 over 32 over 4 factorial, which is just equal to 24. That would become 1 over 32, since the 24's cancel out. 1 over 32 is just equal to 1 over 2 to the fifth, and that would be our final solution. Which of these answer choices provides that option? That would be answer choice B. Welcome and welcome back. I hope you're having a good day as you watch this video. We're going to go over question 25. Which of the following series is or are conditionally convergent? And we are provided with 3 series. I just want to make a mention that if it is conditionally convergent, that means it cannot be absolutely convergent. Absolute convergence, as a reminder, is when the series converges even when the series is not alternating. So let's go through each answer choice it evaluates. Well, if we look at this one, if we pull out the alternator in front and we're just left with 1 over 2 to the n, we see that this represents a geometric series where a is less than 1, which means that this series is a convergent geometric series, which means that it converges absolutely, and thus series 1 is not part of our answer choices possible, which means we can remove choice A, choice B, and choice D. Let's look at series 2 now. Series 2 is different. I'll bring this out in front. Even though each term in the series is discrete, and you can only have whole integer inputs, we can extract the function itself, in which case we say f of n is equal to 1 over square root of n without the alternator in front. For the series to be conditionally convergent, we have to see, does an plus 1, is it always less than a of our current term? And the way we do that is we take the limits as n approaches infinity of 1 over the square root of n. And as we can see, this does approach 0, which means that over time, these values, they start large and then they get smaller. Thus, this condition is satisfied and the series is alternating, which means that series 2 is conditionally convergent. Now, that means that we can immediately rule out answer choice E, and we're just left with answer choice C as our final option. But just to confirm, let's go over the third series. We have f of n is equal to 1 over ln of n. The same rules apply. We take the limit of this function as n approaches infinity of 1 over ln of n, and we find that this value also approaches 0. And it starts positive, or it starts as non-zero. Thus, this function, because it is both an alternating series with the negative 1 to the n out front, and for each term, it's less than the previous term. Thus, we can consider this to be conditionally convergent as well. Thus, we can conclude that the correct answer choice for this problem is C.